Hello and welcome back. In our last video we were talking about second order homogeneous linear equations with constant coefficients. We saw the general form, the characteristic equation, and the two cases we already discussed when the roots of characteristic equation are real and distinct or the roots are equal. In this video we are going to talk about the case when the roots are complex. So when roots are real and distinct, we know the general formula is given by yx equal to c1 e power r1x plus c2 e power r2x, where r1 and r2 are two roots of characteristic equation. And when roots are equal, the general formula is given by yx equal to c1 plus c2x times e power rx, where r is the repeated root. Today we are going to talk about the case when roots of characteristic equation are complex. So we are going to talk about complex roots. So before going into that, let's discuss a little bit about the complex numbers. So you have studied complex number already in your college algebra class. So I'm just going to recall it little bit. So we know we defined square root of -1 as iota. We denote it by I. So if we have any other negative number inside the square root, so suppose we have square root 49, so we can write it as square root -1 times square root 49. Square root 49 is 7, so we can say 7i. So defining square root of -1 equal to I, we basically defined the square root for all negative numbers. Okay, so we just need to remember actually this one little thing, that square root of -1 we are denoting by I. We call it iota. And then complex numbers are basically very simple. Let's see some exercises to know some basic properties of complex numbers. So what is I square? It's going to be I times I. Square root of 1 times square root of 1. So -1. I cube. It's going to be I square times I. I square is -1 times I is going to be -I, right? I power 4. I cube times I. So I cube is -I times I. So we have -I square, and I square is -1, so we will get equal to 1. So two things we can take out from here is I square is -1 and I power 4 is 1, and basically any power we can calculate with the help of this information. Okay. What is 1 over I? So these are actually all the exercises in your notes. So if we want to calculate 1 over I, what we can do is we can multiply and divide by I. So we multiply by I, we divide by I, so we'll get I over I square. I square is -1, so it's equal to -I. So 1 over I is equal to -I. Let's see product of two complex numbers. Suppose we have 1 plus I times 2 minus 3i. How we do the product? We use the same rule, the distribution rules. So 1 times 2 is equal to 2. 1 times -3i is equal to -3i. And then we distribute I. So I times 2 is 2i. I times negative 3i is negative 3i square. So we have negative 3i plus 2i. So we are combining the like terms. So negative 3 minus 2 is negative 1. So we have negative 1. I square is negative 1. So we have 3. So we'll get 5 times negative I. It's really simple, right? Okay. Yeah. So all these properties you can just easily verify. All you need to remember is that square root of negative I, square root of negative 1, square root of negative 1 is I. That's all we need. Okay. Let's talk about one more thing. What is 1 over 3 times 2i? How do we rationalize, right? So what we do is we multiply this by the conjugate. By conjugate we mean we change the sign of I term. If it's 3 minus 2i, we will multiply and divide by 3 plus 2i. So in the numerator we have 3 plus 2i. In the denominator you multiply 3 minus 2i and 3 plus 2i and verify what you will get. Okay. So what we will get actually is 3 times 3 is 9 plus 6i minus 6i will cancel. Okay, no, that was your job to verify. Let me just directly write down what we will get. So we will get 4, 13. So we will get 13. 3 plus 2i divided by 13. So we have 3 divided by 13 plus 2 divided by 13i. This part without I, we also call it real part. This part with I, we call it imaginary part. Imaginary part of the complex number. Okay. So what we learned is when R is a root of characteristic equation, e power rx is a solution to our ODE. Now suppose we have a complex root. So suppose our root is alpha plus I beta. So by intuition, this should be our solution to the ODE, right? But how do we deal with the imaginary part in the part of exponential? Okay, so this is exponential function. It will be like this. When base are similar, we add the power. So these two are equal. We know e to the power alpha by Taylor series, but what is this thing over here? So this thing is again a complex number, and this can be also dealt by Taylor series very similarly. For this, so if we have the knowledge about e power I beta, we can basically talk about the solutions, right? Okay, so let's see. So here comes our Euler formula. So Euler formula says e power I theta is equal to cosine theta plus I times sine theta. If we have e power negative I theta, we replace I by negative I. no change. So this is what we call Euler formula, and this tells us how to deal when we have imaginary powers. Okay, so basically, so this is our Euler formula. So basically what we learned over here is, if we have a complex root a plus I beta x, this can be written as e power alpha x times e power I beta x, and this I beta x we can write it as cosine beta x plus I times sine beta x using the Euler formula, right? Okay, fair enough. So whenever we have a complex root, they always occur in pair. What do I mean by that is, if alpha plus I beta is a root, then alpha minus I beta is also a root. This can be easily seen in the quadratic formula. We have it like this. So the complex root always come in pairs. Okay, so if y1 is a solution to the ODE and it's given by e power alpha x cosine beta x plus I times sine beta x. So this expression is corresponding to the if alpha plus I beta is a solution, and corresponding to alpha minus I beta we get e power alpha x times cosine beta x minus I times sine beta x. This you can easily verify. Okay, so we have these two linearly independent solutions, y1 and y2. If we know two linearly independent solution of second order ODE, we can easily write down the general solution, right? That's not difficult. It's the complex. This is the general solution is going to be the linear combination of these two solutions. Okay, but if you see here, we have some complex things involved. So we can, what we want is, we want a real solution to our ODE. That's why we are doing all this. So but we have this iota still involved over here. So what we can do is, let's y3 is y1 plus y2 divided by 2. So if you add these two, I sine beta x and negative I sine beta x will cancel out, and we will get e power alpha x times cosine beta x, right? And if we subtract these two, we will get negative 2i e power alpha x sine beta x. Oops. I wanted to say sine beta x. So let's divide by negative 2i. Now y3 and y4 is linear combination of y1 and y2. So y3 and y4 is also a solution. Moreover, y3 and y4 are linearly independent, right? So we can say the general solution. So we have 3 points over here. y3 and y4 are solution because they are linear combination of y1 and y2. Second, they are real. so the general solution is going to be real and they are linearly independent. So our general solution can be written as e power alpha x c1 cosine beta x plus c2 sine beta x. This is the general form of solution when we have complex roots. In the next video we are going to work on some examples. I'll see you some example and I'll show you that working on the roots, when working on the ODE when the roots are complex is actually very easy, and I'm going to show you some two examples basically in the next video. I'll see you in the next video. Bye bye.